Imagine waking up one morning and the sky is wrong. Not cloudy, not stormy. Wrong. The sun is there somewhere, but it's filtered through a haze that turns everything into twilight. The air tastes metallic. Your lungs burn with every breath. And this isn't just happening where you are. It's happening everywhere. Across Africa, across Asia, across the entire planet. The sky is darkening, and it won't stop. 74,000 years ago, this nightmare became reality for our ancestors, and what followed nearly erased humanity from existence entirely. Today, there are 8 billion humans living on Earth. We're in every corner of the globe. We've conquered deserts, scaled mountains, built cities that touch the clouds. We've split atoms and mapped the human genome. We dominate this planet in ways that make us feel invincible, permanent, unstoppable. But 74,000 years ago, there might have been as few as 3,000 humans left alive on the entire planet. Some estimates go as high as 10,000. Either way, you could have fit the entire future of humanity into a modern football stadium with seats to spare. Think about that. Every person you've ever known, every person who's ever lived, everyone who will ever live, all of us trace back to a population smaller than a small town. The question isn't just how did this happen? The question is how the hell did we survive? If you're using this to fall asleep, perfect. That's exactly why I make these, so maybe hit subscribe and tell me where you are and what time it is right now. I read the comments and it's wild. Tokyo at sunrise, London at midnight, someone in Australia watching at lunch. The whole world tuning in at once. Here's what makes this story absolutely haunting. For most of human history, we had no idea this even happened. Nobody knew that humanity had brushed up against extinction and somehow impossibly survived. We went about our lives completely unaware that we were the descendants of maybe 1,000 breeding pairs who refused to give up when everything was telling them to die. The clues were always there, hidden in the most unlikely place. Our DNA. See, humans have something really weird about our genetics. We're incredibly uniform. Dangerously uniform, actually. Take any two humans from opposite sides of the planet, New York and New Zealand, Finland and Fiji. Doesn't matter, they'll be about 99.9% genetically identical. You know what else has genetic diversity that low? Endangered species on the brink of extinction. Compare that to chimpanzees, our closest living relatives. 2 chimps from neighbouring groups in the same forest have more genetic differences than a human from Norway and a human from Nigeria. That's not normal. That's the signature of something catastrophic. Something that killed almost everyone and left only a handful of survivors to rebuild the entire species. For decades, scientists suspected some kind of population bottleneck in our past. But they thought it was probably when modern humans first left Africa around 60,000 years ago. A founder effect. A relatively small group of pioneers leaving their homeland and starting new populations elsewhere. That would explain some of our low genetic diversity. But it didn't explain all of it. The numbers didn't quite add up. Our genetic uniformity was too extreme for a simple migration bottleneck. There had to be something else, something worse. Then, in the 1990s, researchers started finding evidence of a catastrophic volcanic eruption at Lake Toba in Indonesia. Not just any eruption, the largest volcanic explosion Earth has seen in 25 million years. An eruption so massive it ejected 2,800 cubic kilometers of material into the atmosphere. For scale, that's about 2,000 times larger than Mount St. Helens. This was an extinction-level event, and it happened exactly 74,000 years ago. right when genetic models suggested human populations crashed to critically low levels. The pieces started coming together like a horrifying puzzle. Genetic evidence of a severe bottleneck, geological evidence of a supervolcanic eruption, climate data showing the planet plunged into a volcanic winter that lasted years, maybe decades, and archaeological evidence showing a massive gap in human activity right around this time period. This wasn't coincidence, this was cause and effect. The Toba eruption nearly killed us all. But here's what keeps scientists up at night. A volcanic eruption, even one as massive as Toba, only creates immediate devastation for a few years, maybe a decade or two. The genetic evidence suggests human populations stayed at dangerously low levels for much longer, potentially 1,000 years or more, which means the eruption wasn't the end of the crisis, it was just the beginning. What followed was a cascade of environmental disasters that pushed humanity to the absolute edge of extinction and held us there while countless other species vanished forever. This is the story of how humanity almost disappeared, and how a tiny group of survivors scattered across a planet turned hostile managed to keep our species alive long enough to inherit the Earth. So what exactly happened 74,000 years ago that pushed humanity to the absolute brink of extinction? What kind of catastrophe could reduce our entire species to just over 1,000 breeding individuals scattered across a continent? The answer is written in the rocks of modern-day Sumatra, Indonesia, in a geological scar so massive you can see it from space. It's called Lake Toba, and 74,000 years ago, it wasn't a lake at all. It was the site of the most violent volcanic eruption in the last 2 million years. Now, when most people think of volcanic eruptions, they're picturing something like Mount Vesuvius burying Pompeii, or maybe the 1980 eruption of Mount St. Helens. Those were devastating events. Thousands died at Pompeii. The Mount St. Helens blast was heard hundreds of miles away and killed 57 people. But Toba wasn't even in the same category. It wasn't a volcanic eruption, it was a supervolcanic eruption, and the difference between the two is like comparing a firecracker to a nuclear bomb. Here's what makes a supervolcano different from a regular volcano. Most volcanoes you've seen pictures of, the classic cone-shaped mountains, they're basically pressure relief valves for the Earth's interior. Magma builds up underground, finds a weak point in the crust, and erupts through a relatively narrow vent at the top of a mountain. Dramatic, sure. Dangerous, absolutely, but ultimately constrained by the size of the opening through which the magma can escape. A supervolcano works differently. Instead of a single vent, you're dealing with a massive underground magma chamber. We're talking about a reservoir of molten rock the size of a mountain range, sitting just a few miles below the Earth's surface, slowly accumulating over tens of thousands of years. The rock above this chamber becomes increasingly stressed, stretched like a balloon being inflated beyond its capacity. Eventually, something has to give. When a supervolcano erupts, it doesn't just blow its top. The entire roof of the magma chamber collapses. Imagine punching a hole in the bottom of a swimming pool, except the pool is 50 miles across and filled with superheated rock instead of water. The result isn't an eruption in the traditional sense. It's a planetary-scale explosion that makes regular volcanoes look like birthday candles. Toba had been building toward this moment for millennia. The magma chamber beneath Sumatra had been filling, expanding, pressurizing. Small earthquakes probably shook the region for years before the main event. Maybe there were warning eruptions, smaller blasts that sent nearby populations fleeing. Or maybe the whole thing happened with terrifying suddenness on what had seemed like an ordinary day. Either way, When Toba finally let go, the result was apocalyptic. The eruption ejected approximately 2,800 cubic kilometers of material into the atmosphere. To put that in perspective, that's enough material to bury the entire state of California under a layer of volcanic debris 12 feet deep. It's 5,000 times larger than the 1980 Mount St. Helens eruption. It's 100 times larger than the eruption of Krakatoa in 1883, which killed 36,000 people and was heard 3,000 miles away. The blast column, the vertical tower of ash and gas shooting into the sky, probably reached heights of 50 to 80 kilometers. That's not just into the stratosphere, that's into the mesosphere, the layer of atmosphere where meteors burn up. Material was being launched with such force that it achieved escape velocity from normal atmospheric circulation patterns. Within hours, a mushroom cloud, larger than any nuclear weapon ever tested, had formed over Southeast Asia. Lightning flickered constantly through the ash cloud, generated by the friction of billions of particles colliding in the turbulent air. The sound of the eruption would have been beyond anything human ears had ever experienced. If there were people within a few hundred miles, they probably died instantly from the pressure wave alone. The pyroclastic flows, avalanches of superheated gas and volcanic debris moving at hundreds of miles per hour, radiated outward from the blast site. These flows could maintain temperatures of 700 degrees Celsius and travel over water, devastating everything within a radius of roughly 3,000 kilometers. That's about the distance from New York to Los Angeles. Everything in that zone, every plant, every animal, every human, would have been incinerated in minutes. But the pyroclastic flows were just the beginning. The immediate kill zone was devastating, but it was still limited to Southeast Asia. The real global catastrophe came from what happened next. Remember those 2,800 cubic kilometers of material that got launched into the upper atmosphere? It didn't just fall back down immediately. The finest particles, microscopic shards of volcanic glass and sulfur compounds, remained suspended in the stratosphere. And because they were above the normal weather patterns, above the clouds where rain could wash them out, they started spreading across the entire planet. Within weeks, prevailing stratospheric winds had carried Toba's ash across the equator and into both hemispheres. Within months, the entire Earth was wrapped in a veil of volcanic particles, and that's when the temperature started to drop. See, volcanic ash in the upper atmosphere does something terrifying. It blocks sunlight. Not all of it, but enough to matter, enough to change everything. The particles act like billions of tiny mirrors, reflecting incoming solar radiation back into space before it can reach the Earth's surface and warm the planet. Scientists estimate that Toba's eruption reduced global temperatures by 3 to 5 degrees Celsius on average. Some models suggest the cooling might have been even more severe, perhaps as much as 10 degrees in some regions. Now, 3 to 5 degrees might not sound like much, but we're not talking about whether you need a jacket today. We're talking about a global average, a shift that affects every ecosystem, every weather pattern, every growing season on the planet simultaneously. The immediate effect would have been the darkening of the sky. For weeks or months after the eruption, sunlight filtering through the ash cloud would have given everything a dim, twilight quality even at midday. Sunrises and sunsets would have been spectacular, painted in deep reds and purples by the light scattering through the debris. Beautiful in a terrible sort of way. But those spectacular sunsets were also a warning. They meant that much of the sun's energy wasn't reaching the ground anymore. temperatures began dropping within the first year. The effect would have been noticed first at higher latitudes and higher elevations, the places already closest to their climate tolerance limits. In the far north and south, regions that were already experiencing Ice Age conditions got dramatically worse. Glaciers that had been slowly advancing suddenly surged forward, grinding down anything in their path. But the tropics suffered too. Regions that had never experienced frost suddenly faced freezing temperatures during winter months. Plants that had evolved for stable warm conditions couldn't adapt fast enough. Die-offs began almost immediately. The volcanic winter lasted approximately 6 to 10 years, almost a decade where global temperatures remained significantly depressed, where growing seasons were shortened, where rainfall patterns were disrupted. For the first 2 or 3 years, it would have been especially bad. That's how long it took for the heaviest ash particles to finally settle out of the atmosphere. During that time, agricultural societies, if any had existed, would have collapsed completely. But humans 74,000 years ago weren't farmers yet. They were hunter-gatherers, dependent on wild plants and animals, and those wild populations were dying en masse. The cooling affected different regions differently. Some areas, like the tropics near major ocean currents, might have experienced relatively mild temperature drops. Others, particularly continental interiors far from moderating ocean influences, would have seen catastrophic changes. Places that had been temperate grasslands transformed into frozen tundra within a few years. The evidence for this climate disaster is written in ice cores from Greenland and Antarctica. Scientists drilling down through thousands of years of accumulated snow can read the climate history of Earth like a timeline, and at the 74,000-year mark there's a clear signature, a layer of volcanic ash, identifiable through chemical analysis as coming from Toba, and immediately following that ash layer, a sharp spike in indicators of global cooling. Tree ring data, where available from that period, tells the same story. Abnormally narrow growth, rings indicating multiple years of harsh conditions. Pollen records from lake sediments show dramatic shifts in vegetation, with cold-adapted species suddenly appearing in regions where they'd been absent for millennia. But perhaps the most vivid evidence comes from the geological scar the eruption left behind. After Toba erupted, after 2,800 cubic kilometers of material had been blasted into the atmosphere, what remained was a hole, a cavity where the magma chamber had been, now that its roof had collapsed inward. This hole, this caldera, is enormous. It measures roughly 100 kilometers long and 30 kilometers wide. Over the millennia since the eruption, it filled with water, creating what we now know as Lake Toba, one of the largest and deepest volcanic lakes on Earth. The lake is over 500 meters deep in places, surrounded by cliffs that mark the edge of the ancient caldera. Today, if you visit Lake Toba, it's actually quite beautiful. A tourist destination. People swim in its waters, fish from its shores, live in villages around its perimeter. But if you know what you're looking at, the landscape tells a story of incomprehensible violence. Those cliffs aren't just scenic viewpoints. They're the walls of an explosion crater so large it can hold a body of water the size of a small sea. In the middle of the lake, there's an island called Samosir, roughly the size of Singapore. That island is actually a resurgent dome, formed when magma started accumulating beneath the caldera floor again after the eruption. It's a reminder that Toba isn't extinct, it's just resting. The magma chamber is filling again, slowly, inexorably. One day, perhaps tens of thousands of years from now, perhaps sooner, Toba will erupt again. But 74,000 years ago, the people living through the eruption's aftermath couldn't see the geological long view. All they knew was that the world had gone dark and cold. The animals they hunted were dying. The plants they gathered were failing, and there was no end in sight. The thing about volcanic winters is that they don't just affect temperature, they disrupt the entire climate system. Monsoon patterns that populations depended on for seasonal rainfall shifted or failed entirely. Ocean temperatures dropped, affecting fish populations and coastal ecosystems. The fine ash particles, even after the worst of them settled out, continued to affect weather patterns for years. In some regions, the ashfall itself was catastrophic. Volcanic ash isn't like snow. It doesn't melt. It's basically powdered rock and glass, and when it accumulates more than a few centimeters deep, it makes the landscape effectively uninhabitable. Plants can't grow through it. Water sources become contaminated. The ash gets into everything, abrading tools, damaging shelters, making it difficult to breathe if stirred up by wind. Archaeological evidence suggests that human populations across a huge swathe of Asia were dramatically reduced or completely eliminated. Sites that show continuous occupation for thousands of years before Toba suddenly go silent, with no evidence of human presence for generations afterward. India, which would have been relatively close to the eruption and downwind of the initial ashfall, shows particularly stark evidence of population collapse. Some archaeological sites are buried under layers of Toba ash up to 6 meters deep. Anything living in those regions when the eruption occurred would have been buried alive. Even populations that survived the initial ashfall still had to contend with the volcanic winter. And here's where it gets really interesting in terms of human evolution. Because this wasn't just a disaster that killed a lot of people. This was a selection event of unprecedented intensity. The only humans who survived were the ones with some combination of luck, intelligence, and adaptability that let them endure conditions that killed 99% of their species. They had to be resourceful enough to find food when their traditional food sources disappeared. Innovative enough to develop new survival strategies on the fly, socially cohesive enough to maintain cooperation when every instinct screamed to hoard resources for yourself and your immediate family, and tough enough, physically and mentally, to keep going through years of hardship that would break most people. The survivors weren't a random sample of humanity. They were the toughest, smartest, most adaptable individuals from populations that had already been tested by the Ice Age climate instability. Toba didn't just reduce human numbers, it filtered humanity through a sieve that only let the most remarkable individuals pass through. And when those survivors finally emerged from the volcanic winter, when the ash finally settled and the sun finally broke through and temperatures slowly began to recover, they were different, changed by the experience, carrying genes that had been tested under the most extreme conditions Earth could throw at them. They were the 1,280, the breeding individuals that genetic analysis tells us humanity was reduced to, the ancestors of everyone alive today, the people who looked at a world devastated by the worst volcanic eruption in 2 million years, and somehow found a way to survive anyway. But surviving the eruption was just the beginning, because the volcanic winter didn't just last 6 to 10 years, and then everything went back to normal. The climate disruption triggered by Toba cascaded through Earth's systems in ways that would affect the planet for thousands of years. And for those scattered populations of survivors, the real test was just beginning. But the eruption itself was only the beginning. What came next was worse, much worse. Within hours of Toba's explosion, Something unprecedented was happening in the upper atmosphere. All that sulfur dioxide, millions upon millions of tons of it, was rising higher and higher, pushed by the heat of the eruption itself, climbing through the troposphere where normal weather happens, passing through the boundary layer, and finally settling into the stratosphere, that quiet, stable zone 10 to 50 kilometers above Earth's surface, where air currents can carry particles around the entire planet. And that's exactly what happened. Within weeks, high-altitude winds had spread Toba's sulfur dioxide in a thin veil across the entire northern hemisphere. Within months, it had encircled the globe. This wasn't just pollution. This was Earth's thermostat being thrown into reverse. Here's what made it so catastrophic. Sulfur dioxide in the stratosphere doesn't just sit there. It reacts with water vapor to form tiny droplets of sulfuric acid. Millions of microscopic mirrors suspended in the air, each one reflecting a tiny fraction of the sun's light back into space. Individually they're nothing. Collectively they're a planetary air conditioner set to maximum. The cooling started almost immediately, not all at once, not everywhere equally, but relentlessly. Global average temperatures dropped by 3 to 5 degrees Celsius. That might not sound like much. It's less than the difference between a warm day and a cool day. But we're talking about averages across the entire planet, sustained for years, and in some regions, particularly at high latitudes and high altitudes, the drop was far more severe. 10 degrees, 15 degrees, enough to fundamentally transform entire ecosystems in a single season. Picture what this means in practical terms. You're a human living in East Africa, maybe in the highlands of Ethiopia, where some scientists think a few groups managed to survive. The eruption happened in late summer. At first, you might not have noticed much beyond the strange colours in the sky and the fine ash coating everything. Then autumn comes, and it's noticeably colder than usual. The rains that should arrive in October are lighter, shorter, less reliable. By January, you're experiencing cold like you've never known. Frost, maybe even snow in areas that haven't seen it in living memory. And it doesn't stop. Spring arrives, but it's not really spring. The growing season that should restore the grasslands and bring back the animals is truncated, colder than normal, with less sunlight filtering through the sulfuric haze that still hangs in the stratosphere. Plants that survived the ash fall are struggling now with the cold and the reduced light. Many species can't complete their life cycles. They germinate, maybe even flower, but fail to produce seeds before the early cold snaps kill them. This is where the real horror of volcanic winter begins. Not in the dramatic explosion, not in the falling ash, but in the slow, grinding collapse of photosynthesis itself. Plants need sunlight, carbon dioxide, and water to produce the sugars that fuel all life on Earth. When you reduce incoming sunlight by even 20 or 30%, you don't just get slightly less plant growth. You get a fundamental breakdown of entire ecosystems. Plants that were already stressed by the ash deposits and acid rain now face months or even years of reduced light. Many species that normally live right at the edge of their environmental tolerances, in areas where conditions are just barely good enough for survival, they start dying. Not all at once, but year after year, as the volcanic winter grinds on, and there's simply not enough energy in the system to sustain them. The archaeological record from this period is sparse, which itself tells a story. But what we do have is revealing. Pollen cores from lake sediments show dramatic shifts in plant communities around 74,000 years ago. Species that had dominated for millennia suddenly vanish from the record or become rare. They're replaced by cold-tolerant species. often plants that normally lived at higher elevations or latitudes, moving into newly cooled territories. Animal populations crashed even harder. Herbivores depend on plant productivity. When the total amount of edible plant material drops by 30, 40, maybe 50% in some regions, herbivore populations have to drop proportionally. There's simply not enough food to sustain the same number of animals. The big grazers, the ones that need the most food, megafauna like ancient elephants and giant antelopes, they're hit first and hardest. Archaeological sites show a dramatic decline in megafauna remains right around the Toba event. Species that had been common become rare or disappear entirely from certain regions, and then the carnivores start dying. Predators are always more vulnerable than prey to food chain collapse because they're at the top of the pyramid. It takes roughly 10 pounds of plants to produce 1 pound of herbivore, and 10 pounds of herbivore to produce 1 pound of carnivore. When plant productivity drops by half, carnivore populations don't just drop by half. They can crash by 75% or more as the entire food pyramid beneath them shrinks. For humans, who were omnivores but increasingly dependent on meat from hunting, this was catastrophic. You're not just competing with other predators for dwindling prey. You're watching the prey itself vanish. The herds of antelope that your people have hunted for generations are getting smaller, more scattered, harder to find. The reliable game trails are empty. The waterholes where animals used to gather predictably are abandoned because the animals are dead or moved to some other region you don't know about. And it's not just the big animals. The small ones suffer too. Rodents, birds, reptiles, all the species that humans could fall back on when big game was scarce, they're declining as well. Some birds migrate away to less affected regions, others fail to breed successfully in the colder conditions. Rodent populations crash when the seeds they depend on don't mature. The fossil record from caves in India, thousands of miles from Toba but directly downwind of the eruption, shows something remarkable and terrible. Before the eruption, these caves contain diverse assemblages of animal bones. Monkeys, rodents, bats, carnivores, a full complement of tropical forest species. Right after the Toba ash layer, that diversity crashes. Some species disappear entirely from the record. Others become rare. The ecosystem composition shifts towards species that can tolerate colder, drier conditions. Now imagine you're one of the humans trying to survive this. You've already endured the initial ashfall. You've survived. The immediate aftermath with its choking air and contaminated water. You think maybe the worst is over. Then the volcanic winter sets in, and you realize the real crisis is just beginning. Your group's traditional hunting territories are failing. The seasonal rounds that your people have followed for generations, moving between different resource zones as plants and animals became available, that whole system is breaking down. You arrive at a location where there should be ripe fruits or tubers, and there's nothing. The plants didn't fruit this year. Or they did, but so weakly that the harvest isn't worth the energy of digging them up. So you adapt. You have to. You start eating things your people wouldn't normally consider food. Plants that require extensive processing to make them edible. Boiling them multiple times to remove toxins. Insects when you can find them. Shellfish from coastal areas, if you're lucky enough to live near a coastline. Marine ecosystems were less affected by the volcanic winter because ocean water has enormous thermal inertia. It takes a lot to cool down the ocean. Coastal populations probably had a real advantage, but most human groups weren't coastal. They were inland, in savannas and woodlands and highlands that were being transformed by the cold, and they were starving. not necessarily acute starvation where everyone dies in weeks. More often, chronic malnutrition where women stop menstruating, where children's growth is stunted, where infections that would normally be fought off become deadly because immune systems are weakened. The thing about volcanic winters is they're unpredictable in their severity. The sulfuric acid aerosols in the stratosphere gradually settle out over time, washing out in rainfall, falling as dry deposition. The cooling should ease after a few years, but Toba was so massive that the aerosol cloud might have persisted for 5, maybe 10 years in significant concentrations, and even after it cleared, the climate system had been knocked into a new state. Remember, Toba erupted during an ice age, a period when Earth's climate was already cooler and more unstable than today. The volcanic winter didn't just cool things down temporarily. It may have triggered feedback loops that kept things cold for decades or even centuries. Snow and ice that formed during the coldest years reflected even more sunlight, creating additional cooling. Ocean circulation patterns may have shifted, altering heat distribution around the planet. Different regions experienced the volcanic winter very differently. Near the equator, where there was more incoming sunlight to begin with, the cooling was significant, but perhaps not completely devastating. Tropical regions may have become more like temperate zones, uncomfortable, challenging, but survivable for populations that could adapt quickly. At higher latitudes, the effects were exponentially worse. Northern Europe, Central Asia, regions that were already cold, during the Ice Age they became nearly uninhabitable. Archaeological evidence suggests that human populations in these areas, if they existed at all before Toba, disappeared entirely afterward. The climate had simply become too harsh to sustain human life with the technology available at the time. High-altitude regions face similar challenges. Mountain valleys that had been marginal for human habitation became impossible. The permanent snowline dropped by hundreds of meters. Growing seasons shrank to nothing. Any humans living in these areas had to move or die. But here's what's remarkable. Some populations found refugia, small pockets where local geography created microclimates that were less affected by the global cooling. Maybe a valley that funneled warm air from lower elevations. Maybe a coastal area where ocean currents still brought warm water. Maybe a region where volcanic soil, ironically, created particularly fertile conditions that partially offset the reduced growing season. These refugia became lifeboats. Small areas, maybe just a few hundred square kilometers, where ecosystems remained productive enough to sustain small human populations. The people living in these areas were lucky in their geography, but they still had to be incredibly resourceful. They had to exploit every possible food source, develop new technologies for extracting nutrition from challenging environments, maintain social cooperation under extreme stress. And they had to do this not just for one generation, not just through one bad year, but for decades at minimum, possibly for centuries as the climate remained locked in a colder state, even after the volcanic aerosols cleared. The volcanic winter was the initial shock, but the climate disruption it triggered was the long-term killer, the thing that kept human populations suppressed for thousands of years, prevented recovery, kept pushing groups toward extinction. This is what environmental catastrophe really looks like. Not dramatic and sudden, but grinding and relentless. Not a single terrible day, but years and decades of slowly worsening conditions where every generation is worse off than the last, where the old survival strategies stop working and new ones have to be invented under desperate conditions. The volcanic winter didn't kill 99% of humanity in a single season. It created conditions that made survival nearly impossible for generation after generation. conditions that slowly ground down human population numbers until only the most adaptable, the most fortunate, the most cooperative groups remained. Those survivors, your ancestors, endured something most species couldn't. They lived through the worst environmental disaster in human history and came out the other side fundamentally changed, shaped by the experience, carrying genetic and cultural adaptations that would define our species forever. But first, they had to survive, and the archaeological evidence of how they did it is written in their DNA. Now here's where this story gets really strange. Because the only reason we know any of this happened is because we can read it, not in books or ancient writings. Those didn't exist yet. We can read it in something far more permanent, far more revealing. We can read humanity's near-death experience in our DNA. Every single person alive today carries the evidence. It's written into every cell of your body. A genetic signature that screams something catastrophic happened to our species approximately 74,000 years ago. And once you know what to look for, the evidence is impossible to ignore. Let me explain how this works, because understanding genetic bottlenecks is like learning to read a new language. Once you get it, you realize our DNA is basically a detailed history book, recording every disaster, every migration, every close call our ancestors survived. Think of genetic diversity as a library. The more books you have, the more information is available. In species that have never faced extinction threats, the genetic library is vast. Chimpanzees, for example, have been around for about 6 million years with relatively stable populations. Their genetic library is enormous. Thousands upon thousands of different genetic variants that make each individual unique. Now imagine a fire that destroys 99% of that library. Only a few books survive. Sure, you can make copies of those surviving books. You can rebuild the library. But the information that was lost is gone forever. No matter how many copies you make, you're just duplicating the same limited content. That's a genetic bottleneck, and humans have the smallest genetic library of any great ape species on Earth. This isn't subtle. The numbers are staggering. Take any two humans from anywhere on the planet, could be from different continents, different ethnic groups, people whose ancestors haven't shared a common homeland for tens of thousands of years. Test their DNA. You know what you'll find? They're more genetically similar than two chimpanzees from the same forest in Africa. Think about that for a second. Two chimps who live within a few miles of each other have more genetic differences than a human from Iceland and a human from Australia. That's not normal. That's the signature of a species that almost went extinct. The genetic evidence comes from multiple independent sources, each one telling the same basic story. Let's start with the most famous, mitochondrial Eve and Y-chromosomal Adam. Now, these names are misleading. They weren't the first humans. They weren't even the only humans alive at their time. But they were the last common ancestors whose genetic lineages survived to the present day through unbroken maternal and paternal lines. Here's what that means. Mitochondrial DNA passes only from mothers to children. It doesn't mix with the father's DNA, so it provides a clean lineage you can trace backward through time. When scientists analyzed mitochondrial DNA from people all over the world, they made a startling discovery. All human mitochondrial DNA traces back to a single woman who lived in Africa between 150,000 and 200,000 years ago. But wait, it gets weirder. Y chromosomes pass only from fathers to sons. When scientists analyzed Y chromosome DNA from men around the world, they found all modern Y chromosomes trace back to a single man who lived between 180,000 and 280,000 years ago. Now, here's the critical part. These weren't the only people alive at that time. There were other women, other men. But every other maternal lineage, every other paternal lineage went extinct. Their descendants died out or had only sons or only daughters, breaking the chain. Only the lineages from these two individuals survived whatever horrors humanity faced in those crucial periods. And when you zoom in on the period around 74,000 years ago, something dramatic shows up in the genetic data. A sudden, severe restriction in both maternal and paternal lineages. Not a gradual decline, a sharp, brutal contraction that looks exactly like what you'd expect if human populations suddenly crashed to near extinction levels. But the evidence goes deeper, much deeper. Scientists can actually estimate ancient population sizes by looking at genetic diversity. The math is complex, but the principle is straightforward. More genetic variation means larger populations. Less variation means smaller populations. It's like counting how many different stories exist in that library we talked about earlier. When researchers applied these techniques to human DNA, they got results that should have been impossible. Multiple studies using different methodologies kept arriving at the same shocking conclusion. Around 70,000 to 80,000 years ago, the effective breeding population of humans dropped to somewhere between 3,000 and 10,000 individuals worldwide. The effective breeding population. That means reproductive adults who were actually having children that survived to reproductive age themselves. The total population might have been higher, maybe 15,000 to 30,000 if you count children and elderly individuals. But in terms of the genetic diversity being passed to future generations, humanity had collapsed to a few thousand people. Some studies suggested even lower numbers. One controversial 2008 analysis estimated the bottleneck might have reduced human populations to as few as 2,000 individuals. That's not a population, that's a small town. Now, not everyone agrees with these numbers. Science rarely involves unanimous agreement, especially when you're trying to reconstruct events from 74,000 years ago using indirect evidence. Some researchers argue the bottleneck was less severe, that populations might have dropped to 10,000 or even 20,000 breeding individuals. Others suggest the genetic patterns could be explained by population structure rather than as actual bottleneck. Maybe humans were divided into small, isolated groups that didn't interbreed much, creating the appearance of low diversity without an actual die-off. But here's the thing, even the most conservative estimates describe a population crash that should have terrified any species. And most analyses keep pointing back to the same period, the same time frame when Toba erupted and the climate went haywire. The genetic evidence shows something else too, something that reveals just how close to extinction we came. Humans lack what geneticists call haplotype diversity. Basically, we don't have enough different versions of our genes. Every species has genetic variants, slightly different versions of the same gene. These variants accumulate over time through random mutations. The longer a population exists at stable levels, the more variants accumulate. It's like a molecular clock ticking away, creating diversity generation by generation. Humans should have accumulated variants for millions of years. Our species and its immediate ancestors have been around for at least 2 million years. But when you actually analyze human genetic variants, you find something strange. Most of our genetic diversity is recent, accumulated only within the last 100,000 years or so. It's as if someone reset the clock. As if the vast majority of human genetic diversity that had accumulated over millions of years suddenly disappeared, leaving only a tiny founding population to rebuild everything from scratch. Mountain gorillas, which everyone knows are critically endangered with only about 1,000 individuals remaining, have more genetic diversity than humans. Cheetahs, which went through their own severe bottleneck about 10,000 years ago, show similar patterns to humans. Low diversity, high genetic similarity between individuals, all the signatures of a species that nearly went extinct. We are the cheetahs of the primate world. We just happen to recover better. The genetic analysis also reveals the geography of survival. By looking at which populations have the highest genetic diversity today, scientists can make educated guesses about where the survivors rode out the catastrophe. The highest genetic diversity among modern humans is found in Africa, specifically in East and South Africa. This makes sense. If Toba's impact was most severe in Asia, and climate effects varied by region, African populations might have had slightly better odds. Not good odds, just less catastrophic than elsewhere. But even African populations show the bottleneck signature. Everyone alive today descends from that tiny founding population. The genetic evidence is absolutely clear on this point. There is no human population anywhere on Earth that escaped the bottleneck. We all went through it together. This genetic unity has profound implications. It means that all the racial and ethnic differences we observe among modern humans are incredibly superficial, accumulated only within the last 70,000 years as populations dispersed from Africa and adapted to new environments. We haven't had enough time or enough genetic diversity to become truly different subspecies. Two humans from different continents share about 99.9% of their DNA. The remaining 0.1% accounts for all physical variation, skin color, hair texture, facial features, everything we think of as racial characteristics. But that 0.1% is just surface adaptations. Underneath, we're all nearly identical, all products of the same bottleneck, all descendants of the same few thousand survivors. The genetic data also reveals something about how populations rebounded after the bottleneck, and this is where the story gets hopeful. Around 60,000 to 70,000 years ago, human genetic diversity starts increasing again. Not dramatically at first, but steadily. Population estimates rise from the bottleneck minimum to tens of thousands, then hundreds of thousands. The genetic signature shows population expansion, groups splitting and migrating, people spreading across Africa and eventually beginning the journeys that would populate the entire world. Scientists can track these migrations through genetic markers, specific mutations that arose in specific populations at specific times, then spread as those populations moved and mixed with others. It's like following breadcrumbs through history, except the breadcrumbs are variations in DNA sequences. One of the most important markers is a mutation designated L3, which appears in mitochondrial DNA around 70,000 years ago in East Africa. Every non-African human alive today carries L3 or its derivatives. This tells us that all non-African populations descend from a small group of L3 carriers who left Africa sometime after the bottleneck, probably around 60,000 to 70,000 years ago. That group was small. Genetic analysis suggests maybe a few hundred to a few thousand individuals made the journey out of Africa. They were a subset of the survivors, a tiny splinter group that would eventually populate 3 continents and become the ancestors of billions. But we're getting ahead of ourselves. The point is, the genetic evidence for the bottleneck is overwhelming. Multiple independent lines of evidence, multiple analytical techniques, all pointing to the same conclusion. Approximately 74,000 years ago, something catastrophic happened to humanity. Our populations crashed to levels that would terrify conservation biologists today. We teetered on the edge of extinction. And yet, we survived. That tiny population scattered across Africa, clinging to whatever resources they could find, somehow held on long enough for the climate to stabilize and populations to recover. Every person alive today owes their existence to those survivors. Without them, without their resilience and adaptability and sheer stubborn refusal to go extinct, humans would be nothing but another fossil species, another branch on the evolutionary tree that didn't make it. The genetic evidence also raises uncomfortable questions. How much did we lose? What genetic variants? What potential adaptations? What unique human qualities disappeared during the bottleneck, carried by the millions who died? We'll never know. Those genes are gone forever, lost when their carriers failed to survive the volcanic winter. The human species today represents only a tiny fraction of the genetic diversity that existed before Toba. We're all descended from the lucky ones, or maybe the tough ones. The ones who happened to be in the right place, with the right skills, and just enough resources to survive until the world became livable again. But here's what might be the most important insight from the genetic evidence. Humans today are proof that species can recover from even the most catastrophic population crashes. Give them enough time, enough resources, enough space to rebuild, and even a few thousand survivors can eventually become billions. We are the evidence that extinction isn't inevitable, that even when 99% of a species dies off, that last 1% can be enough, if they're tough enough, if they're smart enough, if they're lucky enough. The genetic signatures written in our DNA are more than just scientific curiosities, they're reminders. Reminders that we've been to the brink before, reminders that we survived, and reminders that we need to be very, very careful, because nothing guarantees we'd be so lucky a second time. So here's the question that keeps archaeologists awake at night. When Toba erupted and the volcanic winter descended, when the sun was blocked out and temperatures plummeted, when most of Africa and Asia became virtually uninhabitable, where exactly were the survivors? Because they weren't just magically floating in space. They were somewhere specific. Real places with real resources that somehow stayed viable when everything around them collapsed. The answer isn't simple, and that's actually a good thing for humanity's survival. Because here's what we know from the genetic evidence. Those roughly 10,000 individuals, maybe only 1,000 to 2,000 breeding pairs, they weren't all huddled together in some magical valley that escaped the catastrophe. That would have been evolutionary suicide. One earthquake, one disease outbreak, one local drought, and humanity would have been finished. No, they were scattered, spread across multiple locations, probably separated by hundreds or even thousands of miles. This is what biologists call a metapopulation structure, and it's exactly what you'd expect from a species trying to survive a global catastrophe. Don't put all your eggs in one basket. Don't put all your humans in one valley. Let's start with what we know for certain. 74,000 years ago, humans were primarily concentrated in Africa. We'd been there for hundreds of thousands of years. It was home. Some groups had already pushed out into the Middle East and parts of Asia, early pioneers testing the boundaries of human expansion. But the vast majority of humanity was still on the African continent when Toba erupted. When the volcanic winter hit, most of these territories became death traps. The interior of Africa, those vast grasslands that had supported thriving human populations for millennia, they dried up almost overnight. The rain stopped. The rivers slowed to trickles. The megafauna that humans had relied on for food either died or migrated to regions humans couldn't reach. Within a few years, maybe within months in some places, the inland territories went from challenging to completely uninhabitable. But not everywhere suffered equally, and this is where geography became destiny. The most likely refuge, the place where the largest number of survivors probably held out, was the southern tip of Africa, specifically the coastal regions along what's now South Africa's southern shore. This area had three massive advantages that made it uniquely suited for survival during the volcanic winter. First, the ocean. When terrestrial food sources collapsed, the ocean kept producing. Fish don't care if the sun is blocked out for 6 years. The marine food chain runs on nutrients from the deep ocean, not on photosynthesis from surface plants. Shellfish, crustaceans, seals, even beached whales, all still available when everything on land was dying. Second, the climate. The southern tip of Africa sits at a unique confluence of ocean currents. The warmer Gulhas current from the Indian Ocean meets the cold Benguela current from the Atlantic. This mixing creates localized weather patterns that can be dramatically different from the continental interior. When the rest of Africa was freezing, these coastal zones remained relatively temperate. Third, the caves. Southern Africa is riddled with cave systems, natural shelters that provided protection from the cold and the ash-filled air. And we're not talking about crude holes in the ground. Some of these caves are massive, capable of sheltering dozens or even hundreds of people. With natural freshwater seeps and openings that face the ocean for easy access to food. The most famous of these refuges is Pinnacle Point, a series of caves perched on cliffs overlooking the Indian Ocean, about 200 miles east of what's now Cape Town. Archaeologists have been excavating these caves for decades, and what they've found is extraordinary. The occupation layers at Pinnacle Point tell a story of continuous human habitation, stretching back over 160,000 years, but the layers corresponding to the Toba eruption period, right around 74,000 years ago, they're special. They show no interruption, no sudden abandonment, no gap in human activity. While the rest of the world was collapsing, the people at Pinnacle Point just kept living. And what were they eating? The archaeological evidence is crystal clear. Shellfish. Thousands upon thousands of shells from mussels, limpets, and other marine mollusks. The people here weren't hunting megafauna anymore, they couldn't. The animals were gone. Instead, they'd adapted to become systematic harvesters of the intertidal zone. Every day, twice a day, when the tide went out, they went down to the rocks and collected whatever the ocean provided. This might not sound impressive, but it represents a major cognitive and cultural shift. Shellfish collecting requires detailed knowledge of tides, seasons, and marine ecology. You need to know which species are safe to eat at which times of year. You need to understand lunar cycles to predict the best collecting times. You need tools, specialized picks and wedges for prying shellfish off rocks. Most importantly, you need a social structure that can organize and regulate resource extraction. Because here's the thing about shellfish. If you harvest them sustainably, they regenerate quickly and can feed a population indefinitely. But if you overharvest, if you take everything every day without letting the populations recover, you destroy your own food source. The people at Pinnacle Point clearly understood this. The shell deposits show evidence of careful management, selective harvesting, seasonal rotation between different collection sites. They were practicing resource management during a global apocalypse. That's not just survival, that's sophisticated cultural adaptation. But Southern Africa wasn't the only refuge. genetic and archaeological evidence suggests survivors also held out in other scattered locations across the continent and beyond. East Africa, particularly the coastal regions of what's now Kenya and Tanzania, shows evidence of continuous human occupation through the Bottleneck period. These areas had the same advantages as southern Africa: ocean access for stable food sources, relatively mild climates moderated by maritime influences, natural shelters in the form of caves and rock overhangs. The archaeological sites here show similar patterns: a shift from big game hunting to intensive use of marine and coastal resources. Tool assemblages dominated by small specialized implements for processing fish and shellfish, rather than large cutting tools for butchering megafauna. Then there's the evidence from Asia. This is where things get really interesting and controversial, because some researchers believe small populations may have survived in refuges as far east as India and Southeast Asia. The genetic evidence is ambiguous. Modern populations in these regions show signs of ancient bottlenecks, but it's hard to tell if these survivors weathered the Toba crisis in place, or if they represent later recolonization from African refugees. The archaeological evidence is equally complicated. There are sites in India that show human occupation before and after Toba, but many have gaps in the occupational layers right around 74,000 years ago. The most promising evidence comes from coastal regions in southern India and Sri Lanka. These areas were actually much larger 74,000 years ago because sea levels were lower during the Ice Age. What's now underwater continental shelf was dry land, providing extensive coastal plains that could have supported human populations. If survivors did hold out in these Asian refuges, they would have faced challenges even more extreme than their African counterparts. They were farther from the equator, so the volcanic winter would have been colder. They were closer to Toba itself, so the initial ashfall would have been heavier. Some models suggest parts of India received ash deposits over 15 feet deep, enough to completely bury forests and fill river valleys. But they had one crucial advantage: fish. The Indian Ocean is one of the most productive marine ecosystems on Earth. Even during the volcanic winter, the ocean would have continued to provide reliable protein sources, and unlike terrestrial game, fish populations would have recovered quickly once conditions improved. The survival strategy in these Asian refuges, if they existed, would have been similar to Africa: coastal living, marine resource exploitation, small mobile groups that could move along the shoreline as resources fluctuated, heavy reliance on shellfish, crustaceans, and nearshore fish species that could be caught with simple technology. There's also intriguing evidence for survival in cave systems far from any coast. In southern Africa, the Kalahari region has several large cave complexes that show signs of human occupation during the Bottleneck period. These refugees would have faced a different set of challenges. No ocean access meant no reliable protein source from marine resources. Instead, survivors here would have depended on underground water sources, small game that sheltered in the same cave systems, and any plants that could survive in the dim, ash-choked conditions. Life in these inland refugees would have been desperate. Populations probably fluctuated wildly, rising when conditions temporarily improved, crashing when resources failed. Some groups certainly went extinct, their genetic lineages ending in unmarked graves or no graves at all, but a few held on just barely, maintaining enough genetic diversity to contribute to humanity's eventual recovery. Now here's where the meta-population structure becomes crucial. Because these scattered refuges, these pockets of survivors spread across thousands of miles, they weren't completely isolated. Even during the worst of the volcanic winter there would have been contact. trade networks for essential resources like stone for tools or ochre for cultural practices, marriage exchanges to maintain genetic diversity, sharing of information about conditions in distant territories. Archaeological evidence shows that even during the Bottleneck period, certain valuable materials were moving hundreds of miles. Obsidian from volcanic sources in East Africa shows up in southern African sites. Shell beads from coastal regions appear in inland caves. This tells us that despite the catastrophic conditions, despite the tiny populations and desperate circumstances, humans maintained their social networks. These connections were probably what saved us, because when one refuge failed, when drought or disease or simple bad luck wiped out a local population, migrants from other refuges could eventually repopulate the empty territory. The genetic mixing from these occasional contacts maintained diversity and prevented the total inbreeding that would have doomed any completely isolated population. But the isolation was real enough to have profound effects. Those 10,000 to 20,000 years of survival in separated refuges, they set the stage for something unprecedented in human evolution. The different survivor groups were beginning to diverge, not enough to become separate species yet, but enough to establish distinct genetic signatures that we can still detect in modern populations. The people who survived in southern Africa, they were developing genetic variants adapted to marine diets, high in omega-3 fatty acids and iodine. Natural selection was favoring individuals with metabolic pathways optimized for processing seafood rather than terrestrial game. The possible survivors in Asia were facing different selection pressures, colder conditions, different disease environments, different available resources. They were beginning to develop their own distinct adaptations. This geographic isolation, these separated refuges, they were the beginning of human diversity. Not racial divisions, those would come much later and are more cultural than genetic. But the foundation of the genetic variation that makes modern humans so adaptable. Each refuge was a laboratory, testing different survival strategies, selecting for different traits. When conditions finally improved, when the volcanic winter ended and humanity began its explosive expansion, these refuge populations would come back into contact. They would interbreed, mixing their hard-won survival genes into a new combined population that carried advantages from all the different refuges. But that was still thousands of years in the future. For now, in the immediate aftermath of Toba, humanity was scattered, barely surviving, clinging to a few precious refuges where the ocean provided what the land could not. Small groups of people huddled in caves or camped on beaches, watching the ash-darkened sky and waiting for the sun to return. They didn't know they were participating in one of the most important events in human evolution. They just knew they were alive, and as long as they stayed alive one more day, found one more meal, raised one more child to adulthood, humanity had a future. So, let's talk about how those 1,280 breeding individuals actually made it through a decade of volcanic winter, followed by 1,000 years of brutal climate instability, followed by tens of thousands of years of environmental chaos. Because surviving isn't just about getting lucky, it's about having exactly the right toolkit, both literally and figuratively, at exactly the right moment. And here's what makes the human survival story so remarkable. We weren't the strongest species around, not even close. Imagine you're a human 74,000 years ago, standing next to a cave bear that weighs 3 times what you do, or watching a pride of lions that are perfectly adapted to hunt in any conditions. On paper, you should have been the first to go extinct, not the last to survive. But you had something those other species didn't. Something that would prove more valuable than strength, speed, or natural weapons. You had a brain that could think its way out of problems that couldn't be solved with muscle. More importantly, you had other humans around you with brains that worked the same way, and together you could accomplish things that would have been impossible alone. This is where social cooperation becomes the ultimate survival technology. Those small groups of 20 or 30 people scattered across the landscape, they weren't just collections of individuals trying to survive. They were integrated social units where every person's knowledge contributed to the group's survival. The elder who remembered where water could be found during the last drought. The young hunter who had figured out a better way to track wounded animals. The woman who had discovered that certain roots could be made edible through careful processing. All of this knowledge was being shared, refined, and passed down through generations. Think about what this means in practical terms. A solitary animal that loses its food source has to figure out a new survival strategy through trial and error, which often means death by error. But a human group facing the same crisis could pool their observations, share their discoveries, and collectively innovate solutions in a single generation. One person notices that shellfish cluster near certain rock formations. Another observes that these shellfish are more abundant after storms. A third figures out how to cook them to make them safer to eat. Within weeks, the entire group has a new reliable food source, and the knowledge spreads to neighboring groups through trade and kinship networks. But social cooperation only works if you can communicate complex information. This is where language becomes not just useful, but absolutely critical for survival. We're not talking about simple warning calls or emotional vocalizations. We're talking about the ability to convey abstract concepts. 3 days walk to the north, past the twisted tree. There's a valley where antelope gather when the dry season starts. That single sentence contains spatial relationships, temporal concepts, specific landmarks, animal behavior predictions, and seasonal awareness. No other species on Earth could communicate that level of detailed, actionable information. During the volcanic winter and its aftermath, this communication ability would have been the difference between life and death. Groups could share information about which plants were still edible, which water sources hadn't been contaminated by ash, where animals had been spotted, which caves offered the best shelter. This knowledge sharing created a kind of collective intelligence that was far more powerful than any individual's understanding. Now, combine this social and linguistic sophistication with tool technology, and you've got a survival advantage that's hard to overstate. Human tools 74,000 years ago were already remarkably sophisticated. We're talking about carefully crafted stone blades that could butcher animals efficiently, wooden spears with fire-hardened points that could bring down large game, scrapers designed to process hides into clothing and shelter materials. But here's the key. Tool-making is a learned behavior. Every child growing up in a human group was being actively taught by experienced toolmakers. They weren't figuring it out from scratch. They were inheriting hundreds of generations of accumulated technical knowledge. And when the volcanic winter hit, this technological inheritance became crucial. Food scarcity meant that every animal killed had to be utilized as completely as possible. Stone tools allowed humans to extract bone marrow, rich in calories and nutrients, that other predators couldn't access. Specialized scrapers could process every scrap of usable hide. Cutting implements could portion meat for drying and preservation. In an environment where a single successful hunt might have to sustain a group for weeks, this level of efficiency was survival itself. But perhaps the most important tool wasn't made of stone. It was fire. and by 74,000 years ago, humans had mastered fire in ways that gave them capabilities that bordered on supernatural from another species' perspective. This wasn't just keeping a naturally occurring fire alive. This was the ability to create fire on demand, to control it, to use it as a tool for multiple purposes. When volcanic ash blocked out the sun and temperatures plummeted, fire provided warmth that kept hypothermia at bay during endless cold nights. Fire extended the day, allowing work and social interaction to continue after darkness fell. Fire protected encampments from predators, creating safe zones where vulnerable children and elders could sleep without guard. But most crucially, fire transformed food possibilities. Raw foods that would have been indigestible or toxic could be cooked into safe, nutritious meals. Tubers, roots, certain leaves, even some kinds of bark could be processed through roasting or boiling to extract calories that would otherwise be unavailable. In a world where food sources were collapsing, this dietary flexibility was everything. Because here's what you need to understand about human dietary adaptability. We are, biologically speaking, omnivores taken to an almost absurd extreme. Humans can't digest grass like herbivores, can't process raw meat as efficiently as carnivores, can't eat tree bark like many animals, but we can eat almost anything if we process it correctly. During the worst years of the volcanic winter, when preferred food sources disappeared, humans could switch between hunting whatever animals remained available, gathering whatever plant foods could be found, and even exploiting food sources that other species ignored entirely. This is where coastal living became a game changer. Archaeological evidence suggests that some of the survivor populations during the Toba Bottleneck were concentrated along coastlines, and it's not hard to see why. While inland ecosystems were collapsing under the stress of climate chaos, coastal zones offered something remarkable: stability. Shellfish populations, tide pools, seaweed beds. These resources were largely unaffected by volcanic ash and temperature fluctuations. Shellfish are basically packages of protein and minerals that sit in one place waiting to be collected. They don't require hunting skills or dangerous confrontations with predators. They're predictable, renewable, and abundant. Better yet, shellfish harvesting is a social activity that the entire group can participate in. Children, adults, elders, everyone can contribute to collecting food during low tide. This meant that even when hunting large game became difficult or impossible, a coastal group could still feed itself reliably. Some researchers think this is why we see a concentration of genetic diversity in African populations that would have had access to coastlines. These were the groups that had stumbled onto one of the most reliable survival strategies available. But coastal living required its own technologies. You needed containers to transport shellfish back to camp. You needed knowledge of tides and seasons to harvest efficiently. You needed cooking techniques to make certain shellfish safe to eat. And you needed the social organization to prevent overexploitation of shellfish beds. Archaeological sites from this period show evidence of systematic harvesting. Not just grabbing every shellfish in sight, but selective collection that allowed populations to regenerate. This suggests our ancestors understood resource management at a level of sophistication that we usually don't associate with Stone Age societies. And then there's clothing and shelter technology. In the volcanic winter, when temperatures dropped and stayed low for years, the ability to create artificial protection from the elements became non-negotiable for survival. Human skin is relatively hairless compared to most mammals. We're terrible at keeping warm naturally. But what we lack in natural insulation, we made up for with artificial insulation. Animal hides, processed and scraped to make them flexible, could be worn as primitive clothing or used as blankets. Archaeological evidence from this period shows increasingly sophisticated hide processing techniques, scraping tools designed specifically for this purpose, bone needles that suggest sewing technology, even possible evidence of using plant fibers to create cordage for binding materials together. When you can create clothing, you can survive in environments that would kill you naked. This opened up cave systems and rock shelters that stayed colder, but offered better protection from weather and predators. Shelter construction was evolving too. Instead of just finding natural caves and hoping they were suitable, humans were modifying shelters to make them more livable, building windbreaks from branches and hides, creating fire pits positioned to maximize warmth and minimize smoke, possibly even constructing simple huts or lean-tos in areas where natural shelter wasn't available. Each of these innovations represented problem-solving, planning, and the application of accumulated knowledge. But here's where the survival story gets really interesting. All of these adaptations, social cooperation, language, tool-making, fire mastery, dietary flexibility, clothing, shelter technology, they weren't separate survival strategies. They were interconnected, each one making the others more effective. Fire improved food processing, which improved nutrition, which gave people energy to make better tools, which improved hunting success, which provided better hides for clothing, which allowed access to better shelters, which improved survival rates, which maintained group size, which allowed for better social cooperation and knowledge sharing, which led to new innovations, which started the cycle over again. This is what biologists call a positive feedback loop. Each adaptation reinforced the others, creating a survival system that was greater than the sum of its parts, and this system was uniquely human. No other species had assembled this particular combination of abilities. Neanderthals had some of these traits, other primates had others, but only humans, only this specific population of survivors, had the complete package. And here's the really wild part. The crisis may have actually accelerated the development of these traits. Natural selection during the Bottleneck wasn't just favouring individuals who were strong or fast. It was favouring individuals who could think creatively, cooperate effectively, communicate clearly, and adapt quickly to changing conditions. The genes associated with higher cognitive function, with social intelligence, with behavioural flexibility. These were the genes that got passed on preferentially during the worst years of the crisis. Some researchers think this is why humans after the Bottleneck show evidence of accelerated brain development and enhanced cognitive abilities compared to our pre-Bottleneck ancestors. The crisis didn't just kill off most of humanity, it selected for the smartest, most adaptable, most cooperative individuals, and their descendants inherited those survival-tested traits. Cultural knowledge transmission played an absolutely crucial role in this selection process. In stable environments, raw survival ability might be enough, but in rapidly changing, unpredictable conditions, the ability to learn quickly and teach effectively becomes paramount. Children who could absorb cultural knowledge faster had better survival prospects. Adults who could teach skills clearly could pass more knowledge to the next generation. Groups that developed better methods for preserving and transmitting information had advantages over groups that didn't. This created selection pressure not just for intelligence in general, but for specific types of intelligence. Social intelligence, the ability to understand and work with other people. Linguistic intelligence, the capacity to use language effectively for complex communication. Practical intelligence, the skill to apply abstract knowledge to real-world problems. All of these were being refined generation after generation during the Bottleneck. By the time the volcanic winter ended and climate conditions began to stabilize, the survivors weren't just lucky. They were evolutionarily optimized for survival under the worst possible conditions. They were humans who'd been stress-tested by nature itself and found worthy. Every survival strategy that didn't work had been eliminated through the brutal process of natural selection. What remained was the core toolkit that would carry humanity not just through the recovery, but through every subsequent crisis we would face. These were our ancestors. Every person alive today is descended from these survivors, from these problem solvers, from these innovators who refused to give up when every environmental factor was telling them to lie down and die. We carry their genes, their adaptations, their hard-won survival strategies in our DNA. We are living proof that sometimes the worst disasters don't destroy a species. Sometimes they forge it into something stronger, smarter, and more resilient than it was before. But survival was just the first chapter. What happened when the climate finally stabilized would change everything about human evolution and set the stage for the world we inhabit today. But here's what we haven't talked about yet. While those 1,280 humans were clinging to survival, fighting every single day to keep their species alive, thousands of other species were losing their own battles with extinction. And most of them didn't make it. The Toba eruption didn't just threaten humanity, it triggered what scientists call a megafaunal decimation event, a mass die-off of large animals across multiple continents, and the casualties were staggering. Start with our closest relatives, the other hominins. See, 74,000 years ago, humans weren't alone. We shared the planet with at least 3 other species of human-like creatures, Homo erectus, who had been successfully living across Asia for nearly 2 million years, Homo floresiensis, the so-called hobbits of Indonesia, barely 3 feet tall but remarkably sophisticated, and possibly late surviving populations of other archaic humans scattered across isolated pockets of Africa and Asia. The volcanic winter killed most of them. Homo erectus populations across Southeast Asia collapsed almost overnight in geological terms. These weren't primitive creatures. They had controlled fire for hundreds of thousands of years. They made sophisticated stone tools. They had successfully colonized territories from Africa to China to Java. They were survivors, tested by time and proven by success. But they hadn't developed the social complexity that saved our species. When the ash fell and the temperatures plummeted, Homo erectus groups were too isolated, too independent. They didn't have the trade networks that connected human populations. They didn't have the information-sharing systems that let knowledge spread across hundreds of miles. When their local resources collapsed, they had nowhere to turn. Most died out within a few generations. The last confirmed Homo erectus fossils date to shortly after the Toba eruption. Coincidence? Probably not. The hobbits lasted longer, protected by their island isolation on Flores. But even they showed signs of population stress. Fossil evidence suggests their numbers crashed dramatically around this period. They survived another 50,000 years before finally going extinct, but they never recovered their pre-Toba population levels. The eruption had wounded them too deeply. Think about that for a second. Species that had survived for hundreds of thousands of years, that had weathered ice ages and droughts and climate shifts, that had proven themselves again and again as evolutionarily successful, they all got wiped out by the same event that nearly killed humanity. The difference. We had developed just enough social complexity, just enough cooperative breeding networks, just enough information sharing to survive. They hadn't, and that tiny difference meant life or death for entire species. But the hominins weren't alone in their suffering. The megafauna, the giant animals that had dominated ecosystems across the world, they got hammered even harder. In Southeast Asia, where the ashfall was thickest, entire species of large mammals vanished. Giant orangutans, apes that stood 8 feet tall and weighed over 600 pounds went extinct. They had lived in the forests of southern China and Vietnam for hundreds of thousands of years, perfectly adapted to their environment. But when the volcanic winter killed the fruit trees they depended on, when the forest died back and the temperatures crashed, they couldn't adapt fast enough. Within a few thousand years they were gone, forever. The giant tapirs of India suffered the same fate. So did the enormous tortoises that had lived on islands across the Indonesian archipelago. Species after species, lineages millions of years old, just snuffed out. Africa saw similar devastation, though the distance from Toba gave some species a fighting chance. But fighting chance didn't mean survival. The giant buffalo that had roamed the savannas, animals with horn spans over 6 feet wide, nearly went extinct. Their populations crashed so hard that genetic analysis shows a bottleneck even more severe than the human one. They survived, barely, but they never recovered their former range or numbers. The few that made it through became the ancestors of the modern African buffalo, smaller, less impressive, but resilient enough to persist in a world that had been fundamentally changed. The great cats faced their own crisis. Lions, leopards, cheetahs, all showed evidence of severe population reductions during this period. And here's where it gets interesting. They were predators, top of the food chain, theoretically better positioned to survive than prey species. But that's not how ecosystem collapse works. When the volcanic winter killed the grasslands, it killed the herbivores that depended on those grasslands. When the herbivores died, the predators that ate them starved. Doesn't matter how fierce you are if there's nothing to hunt. The big cats survived only because they could switch prey, could adapt their hunting strategies, could survive on smaller animals when the big game disappeared. But their populations never fully recovered to pre-Toba levels. Genetic studies of modern lions show they went through a bottleneck around this time that reduced their diversity permanently. The primates, our cousins, they might have had it worst of all. Across Africa and Asia, monkey and ape populations crashed. These were species that depended on consistent fruit production, on stable forest environments, on temperature ranges that didn't swing wildly from year to year. The volcanic winter destroyed all of that. Trees that had produced fruit reliably for thousands of years suddenly stopped. Forests that had been lush and green died back to scrubland. Temperatures that had varied by maybe 10 degrees across the whole year suddenly swung 40 degrees between summer and winter. Most primate species couldn't handle it. They didn't have the dietary flexibility that humans had developed. They couldn't switch from fruit to roots to meat to insects depending on what was available. They were specialists, and specialization is a death sentence when your specialty disappears. Chimpanzee populations in Africa crashed to maybe 10% of their pre-Toba numbers. They survived because they were smart enough, flexible enough, social enough to adapt. But it was close. Gorillas went through an even more severe bottleneck. Genetic analysis suggests some gorilla subspecies were reduced to fewer than 100 individuals. And here's what's heartbreaking. These were our closest relatives. Species that shared over 98% of our DNA. They had many of the same cognitive abilities we did. They could use tools, solve problems, cooperate in complex social groups. But they didn't have quite enough flexibility, quite enough adaptability to weather the storm. We survived. They barely made it, and thousands of other primate species, ones we'll never know about because they went extinct before leaving any fossil record they didn't make it at all. The question is why? What separated the survivors from the extinct? What made the difference between a species that persisted and one that disappeared forever? It comes down to flexibility. Not physical flexibility, but ecological and behavioural flexibility. The ability to eat whatever's available instead of depending on one food source. The ability to live in different environments instead of requiring one specific habitat. The ability to change strategies when conditions change instead of rigidly following inherited behaviours. Humans had all of these in abundance. We were the ultimate generalists. We could eat meat or plants or insects or shellfish. We could live in forests or grasslands or coastlines or mountains. We could invent new tools when old ones didn't work. We could share information across populations, meaning that a survival strategy discovered by one group could spread to others. The species that went extinct were specialists. The giant orangutans needed fruit forests. The mega buffalo needed extensive grasslands. The specialized primates needed stable climates and consistent food sources. When those disappeared, so did they. But some species surprised everyone. Take the elephants. You'd think that massive animals requiring hundreds of pounds of vegetation every single day would be the first to go when the volcanic winter hit. But elephants survived relatively well. Why? Because they were smart and social. They had matriarchal groups that maintained knowledge across generations. They could travel hundreds of miles to find resources. They could eat an incredibly wide variety of plants. They had the behavioural flexibility to adapt. The species that recovered fastest after the volcanic winter were the ones that combined flexibility with rapid reproduction. Rodents exploded in numbers once conditions improved. So did certain types of birds. These weren't the apex predators or the charismatic megafauna. They were the adaptable generalists, the species that could eat anything, live anywhere, and reproduce quickly when conditions permitted. And here's the really wild part. The extinctions and near extinctions caused by Toba fundamentally reshaped Earth's ecosystems. When the megafauna died off, it created ecological vacancies, empty niches that could be filled by whatever species recovered first. In many regions, humans filled those niches. We became the apex predators. We became the primary consumers of large game. We became the species that shaped the environment through our activities. The Toba eruption didn't just almost kill humanity, it created the conditions for humanity's eventual dominance. Every species that went extinct was one less competitor for resources. Every population that crashed was one less threat to human expansion. When our ancestors finally began spreading out after the bottleneck ended, they inherited a world that had been cleared of much of the competition that might have stopped them. It's dark to think about, but it's true. We survived the greatest catastrophe in human history, partly through our own adaptations, but also partly because we got lucky. We were flexible enough to survive when specialists died. We were social enough to maintain populations when isolated species went extinct. And we were positioned to explode into a world that had been depopulated of competitors. The Great Die-Off was a tragedy for thousands of species. But for humanity, it was the crucible that forged us into the dominant species on Earth. Picture this. It's 70,000 years ago. The ash has finally settled. The skies, which had been the colour of rust and death for years, are clearing. The volcanic winter that followed Toba is ending. And somewhere in those scattered refuges, those tiny pockets where humanity clung to existence, Something remarkable is beginning to happen. Children are surviving, not just 1 or 2 per generation, but most of them. Food is becoming more reliable. The megadrought is loosening its grip. Rain is returning to regions that had been bone dry for generations, and those few thousand survivors, those battle-tested, climate-hardened, evolutionarily refined humans, they're about to do something extraordinary. They're going to take over the world. But here's the thing, it didn't happen overnight. This wasn't some Hollywood moment where humanity suddenly bounces back in a single generation. The recovery was slow, painfully, frustratingly, desperately slow. For the first few thousand years after the worst of the volcanic winter ended, human populations probably grew at a crawl, maybe 1 or 2% per generation. Your ancestors were still living in small, scattered groups, still vulnerable to local disasters, still genetically bottlenecked in ways that made survival harder than it should have been. A disease that might wipe out a few individuals in a genetically diverse population could devastate an entire group when everyone was closely related. Inbreeding depression was a constant threat. Birth defects, reduced fertility, lower survival rates. The genetic price of the bottleneck was real, and it was being paid in every generation. But they kept going. Because here's what those 1,000 to 10,000 breeding individuals had that their ancestors didn't. They had knowledge, technologies developed during the crisis years, social systems refined by desperate necessity, cognitive abilities sharpened by tens of thousands of years of the harshest natural selection imaginable. They were smarter, more cooperative, better at solving problems than any humans who had come before them. And slowly, generation by generation, the population began to climb, from a few thousand to tens of thousands. Groups that had been isolated for millennia began making contact again. Trade networks started reforming. Knowledge sharing accelerated. A stone tool innovation developed in one refuge would spread to others within a few generations instead of being lost when the inventor died. By 65,000 years ago, human populations in Africa had probably reached several 100,000. Still small by modern standards, still vulnerable, but no longer teetering on the edge of extinction. The immediate crisis had passed, but the genetic legacy of the bottleneck remained. Every human alive carried the signature of those desperate millennia. Reduced genetic diversity, the specific mutations that had survived the winnowing, the chromosomal patterns that mark them as bottleneck descendants, and then something changed. Something that would reshape the entire human story. They left Africa. Now, humans had left Africa before. There's evidence of earlier migrations going back hundreds of thousands of years. But those early pioneers didn't succeed. They spread into the Middle East, maybe as far as Asia, and then disappeared, outcompeted by other hominins, killed by climate shifts, lost to history. But the post-Toba humans were different. When they left Africa around 60,000 to 70,000 years ago, they didn't just survive, they conquered. This is the out-of-Africa migration that every non-African person today descends from. This is the moment when humanity stopped being an African species and became a global one. The genetic evidence for this is absolutely stunning. When scientists analyze DNA from people around the world, they find something remarkable. All non-African populations show evidence of descending from an incredibly small founding group. We're talking maybe a few hundred individuals who crossed from the Horn of Africa into the Arabian Peninsula. That's it. That's the seed population for billions of humans across 6 continents. This is what geneticists call a founder effect, and it's the bottleneck within the bottleneck. The original Toba survivors had already reduced human genetic diversity. Then a tiny subset of those survivors founded all non-African populations. It's like taking a small sample of a small sample. Each migration out of Africa reduced genetic diversity even further. This is why genetic diversity decreases the farther you get from Africa. Africans have the highest genetic diversity of any human population because they descended from the full range of bottleneck survivors. Middle Eastern populations have slightly less diversity because they descended from the subset that left Africa. Europeans have even less because they descended from the subset that left the Middle East. And so on, population by population, migration by migration, all the way to the Americas, which were settled last and show the lowest genetic diversity of any continent. You can literally trace the migration routes of ancient humans by measuring how genetic diversity decreases. It's like a breadcrumb trail written in DNA, showing exactly where our ancestors went and in what order. But here's where the story gets really wild. Those migrants didn't walk into an empty world. They walked into a world full of other human species. Neanderthals in Europe and Western Asia, Denisovans across Central and Eastern Asia, Homo erectus still hanging on in Southeast Asia, Homo floresiensis, those tiny island-dwelling humans surviving in Indonesia. The world 60,000 years ago was full of humans, just not our kind of humans. And when they met, something happened that would echo through every generation to follow. They interbred. The genetic evidence is undeniable. Modern non-African populations carry Neanderthal DNA, typically about 1 to 2% of their genome. Some Asian and Oceanian populations carry Denisovan DNA, sometimes as much as 4 to 6%. We're all hybrids, all carrying genes from species that no longer exist. But those genes weren't random. Natural selection kept the useful ones and discarded the harmful ones. That Neanderthal DNA you're carrying if you're of European or Asian descent, it's concentrated in genes related to immune function, skin and hair traits, and metabolism. The Neanderthals had been living in Europe and Asia for hundreds of thousands of years. They'd evolved adaptations to those environments. When our ancestors encountered them, interbred with them, and then continued their migrations, they carried those adaptive genes with them. It was like a genetic shortcut. Instead of spending hundreds of thousands of years evolving cold weather adaptations, our ancestors just borrowed them from Neanderthals who'd already done the work. Denisovan DNA in Tibetan populations helps them survive at high altitudes. Denisovan DNA in Oceanian populations might help with fat metabolism. These are genes that survived because they were useful. Genes that help the hybrid descendants of the bottleneck survivors thrive in new environments. And thrive they did. Within just 10,000 years of leaving Africa, humans had spread to Australia. By 45,000 years ago, they were in Europe. By 15,000 years ago, they'd reached the Americas. In evolutionary terms, this is instantaneous. This is a single species spreading across the entire habitable world in what amounts to a geological eye blink. The population grew explosively. From those few hundred initial migrants to millions within a few thousand years. And the growth wasn't linear, it was exponential. Each generation wasn't just slightly larger than the last, it was massively larger. Resources were abundant in these new territories. Megafauna that had never encountered human hunters, plants that could be harvested without competition, coastlines teeming with shellfish, rivers full of fish. Our ancestors walked into ecological paradise after ecological paradise, and they multiplied accordingly. By 10,000 years ago, human populations worldwide probably numbered in the millions. By 5,000 years ago, tens of millions. Today, nearly 8 billion, all descending from those few thousand Toba survivors. But it wasn't just population numbers that exploded, it was innovation, technology, culture. The archaeological record from this period shows something unprecedented in human history, what scientists call the Upper Paleolithic Revolution, a sudden, dramatic increase in the complexity and diversity of human artifacts. Before the Bottleneck recovery, human technology had been relatively static for hundreds of thousands of years. Stone tools improved slowly. Innovation happened, but gradually, incrementally. After the recovery, everything accelerates. New tool types appear: bone and antler tools, needles for sewing clothes, harpoons for fishing, spear throwers that increased hunting range and accuracy, cave paintings, carved figurines, musical instruments, jewelry. These weren't just practical innovations, they were expressions of symbolic thinking, art, culture, the kind of cognitive complexity that separates modern humans from every other species that has ever existed. And they all appeared in the archaeological record right after the Bottleneck recovery, right after human populations began expanding out of Africa. Some scientists think this is no coincidence. They argue that the Toba bottleneck didn't just nearly destroy humanity, it transformed us. The intense selection pressure during those desperate millennia favored certain traits: intelligence, creativity, social cooperation, the ability to innovate under pressure. The humans who survived weren't just lucky, they were the smartest, most adaptable, most cooperative individuals in the population. And when their descendants finally had room to grow, when populations expanded and resources became abundant, all their accumulated intelligence and creativity exploded outward. Innovation built on innovation. Ideas spread between groups. Technologies evolved at unprecedented rates. The bottleneck had created a kind of evolutionary pressure cooker, and when the pressure released, humanity burst forth with capabilities that would let them reshape the entire planet. Think about it this way: every major human achievement, agriculture, writing, mathematics, science, art, all of it was accomplished by descendants of the bottleneck. Every single person who has ever contributed to human civilization carried genes that survived 74,000 years ago. Genes that were refined by fire and ash and desperate struggle. We are not just the descendants of survivors, we are the descendants of the most capable survivors evolution has ever produced. The genetic evidence confirms this in ways that are almost eerie. When scientists analyze the human genome for signs of recent selection, for genes that changed rapidly in the last 100,000 years, they find intense selection on genes related to brain development, cognitive function, language abilities, social behavior, the traits that make us human, the things that separate us from every other primate, show evidence of being under strong selection pressure during and immediately after the bottleneck period. We didn't just survive the bottleneck, we were forged by it, shaped by it, made into something new and unprecedented by the desperate struggle to persist when death seemed certain. And when we finally had the chance to grow, to expand, to fill the world with our descendants, we carried all those hard-won advantages with us. But here's the most remarkable thing. Despite everything, despite the near extinction and the desperate recovery and the explosive expansion across the globe, we're all still fundamentally the same species. The genetic distance between any two humans on Earth today is smaller than the genetic distance between two chimpanzees from neighboring groups in the same forest. The bottleneck made us relatives, all of us. Every human alive today shares ancestors who huddled in these African refugees 74,000 years ago. We are literally family. distant cousins separated by hundreds of generations, but family nonetheless. The same chromosomal fusion, the same genetic signatures, the same legacy of survival against impossible odds. We grew from the brink, from a few thousand desperate survivors to nearly 8 billion, from scattered refugees clinging to marginal environments to the dominant species on the planet, and every step of that journey, every innovation and migration and population expansion was made possible by the legacy of those who survived when survival seemed impossible. That's the story written in our genes. That's the legacy of the Rebound. We are all children of the Bottleneck, all proof that sometimes when everything goes wrong, when the world itself seems to be ending, life finds a way to persist, to grow, to thrive against all odds. But here's where the story gets complicated, because not everyone agrees that Toba nearly ended humanity. In fact, the scientific community has been engaged in an increasingly heated debate about whether this volcanic winter actually caused the genetic bottleneck at all. And the more we learn, the messier the picture becomes. The traditional story sounds perfect, right? Massive volcano erupts 74,000 years ago. Climate collapses. Humans nearly go extinct. Population crashes to a few thousand individuals. We barely survive. It's dramatic, it's compelling, and for years it was the dominant theory in paleoanthropology. But science doesn't care about dramatic stories. Science cares about evidence. And lately, the evidence has been painting a much more complicated picture. The first cracks in the theory appeared in the archaeological record. Starting around 2010, researchers began excavating sites in India, Malaysia, and East Africa that dated to immediately after the Toba eruption. And here's what they found. Nothing happened. Or at least nothing catastrophic. Stone tools from before Toba look essentially identical to stone tools from after Toba. Same designs, same manufacturing techniques, same levels of sophistication. There's no gap in the archaeological record, no dramatic change in technology that would suggest populations had crashed and knowledge had been lost. At the Jwalapuram site in southern India, archaeologists found Middle Paleolithic stone tools in layers both above and below the Toba ash layer. The tools showed continuous occupation with no apparent disruption. People were living there before the eruption, they were still living there after, and they were making the same kinds of tools the whole time. This shouldn't be possible if Toba had caused a catastrophic volcanic winter that wiped out most human populations. Similar findings emerge from sites across Africa and Asia. At Pinnacle Point in South Africa, researchers found evidence of continuous human occupation right through the period when Toba erupted. No population crash, no technology loss, no sign that anything particularly terrible had happened. The people living there just kept doing what they'd been doing, gathering shellfish, making stone tools, maintaining fires. Then the climate scientists weighed in with even more troubling news for the catastrophe theory. New climate models, more sophisticated than the ones used in the 1990s, suggested that Toba's impact on global temperatures might have been significant but not apocalyptic. Instead of a decade-long volcanic winter, with temperatures dropping 15 degrees Celsius, the new models suggested maybe 3 to 5 degrees of cooling lasting perhaps a few years. That's still serious, that's still enough to cause widespread environmental stress, but it's not extinction level. It's not 99.9% of humanity dies level. It's more like, this is going to be a really terrible decade, but we can probably survive it level. Some climate models even suggested the cooling might have been highly regional. The northern hemisphere probably got hammered, especially areas downwind from the eruption. But equatorial Africa, where many of the surviving human populations were likely concentrated, might have experienced much milder effects. The tropical climate there is incredibly stable, buffered by ocean currents and atmospheric circulation, patterns that can dampen the impact of even massive volcanic eruptions. So if Toba didn't cause the bottleneck, what did? Enter the alternative theories. One camp of researchers argues there was no single catastrophic event at all. Instead, they propose multiple smaller bottlenecks spread across hundreds of thousands of years. Climate records from ice cores and ocean sediments show that the period from about 200,000 to 50,000 years ago was incredibly unstable. Rapid swings between warm and cold periods, unpredictable rainfall patterns, frequent droughts in Africa. Under this scenario, human populations were repeatedly squeezed down to small numbers, not all at once but in waves. One drought reduces populations in East Africa. A few thousand years later, populations in southern Africa crash due to a different climate event. Populations recover somewhat, then get hit again by the next crisis. Over hundreds of thousands of years, this repeated stress could produce the same genetic signature as one massive bottleneck. Think of it like this. You can squeeze a population down to 10,000 individuals all at once, or you can squeeze it down to 20,000 individuals 100 different times. Genetically, the end result might look very similar. Lots of genetic diversity gets lost either way, rare alleles disappear, the population ends up looking like it went through a severe restriction. Other researchers have proposed what they call the meta-population bottleneck model. This is more subtle, but potentially more accurate. They argue that human populations in Africa during this period existed as small, semi-isolated groups that rarely interacted. Most breeding happened within groups, with only occasional gene flow between them. Under this model, the effective population size, the number that matters for genetics, could have been very small even if the actual number of living humans was much larger. Maybe there were 50,000 humans alive, but they were divided into hundreds of small groups that barely mixed. Genetically, this produces a signature that looks like a severe bottleneck, even though no catastrophic die-off actually occurred. The genetic evidence itself has become a battleground. Early studies using mitochondrial DNA and Y chromosome analysis suggested a severe bottleneck around 70,000 years ago, which lined up perfectly with Toba. But more recent studies using whole genome sequencing have produced wildly different estimates. Some analyses suggest the bottleneck was earlier, maybe 100,000 or 150,000 years ago, which would rule out Toba as the cause. Others suggest it was much less severe than originally thought. Maybe populations only dropped 10,000 or 20,000, breeding individuals rather than a few thousand. Still others argue that different human populations experience bottlenecks at different times, and what we're seeing in the genetic data is an average across multiple distinct events. Part of the problem is that geneticists have to make a lot of assumptions when they reconstruct ancient population sizes. They assume certain mutation rates, certain patterns of inheritance, certain models of how populations grow and shrink. Change any of these assumptions and you get very different numbers. A 2018 study used a new statistical approach that tried to account for these uncertainties. Their conclusion? The bottleneck was real, but probably not as extreme as the original study suggested. Population size dropped significantly, maybe by 50% to 70%, but not by 19%. And it might have lasted much longer than a single event like Toba would produce, possibly 100,000 years or more of reduced population size. Meanwhile, anthropologists studying fossil evidence have added another wrinkle. The human fossil record from this period is incredibly sparse, which is part of what makes studying it so difficult. But the fossils we do have don't show the kind of drastic population crash you'd expect from a near-extinction event. Human remains from before, during, and after the supposed bottleneck period show considerable diversity in skull shapes and skeletal features. This suggests multiple populations existing in different regions, not a tiny remnant group that barely survived. If humans had really crashed to just a few thousand individuals all living in one small area, we'd expect to see much less diversity in the fossils. So where does all this leave us? The honest answer is that we don't know for sure. The debate is ongoing, sometimes contentious, and far from resolved. The most moderate view, which is gaining support among many researchers, goes something like this. Yes, human populations went through one or more severe bottlenecks between about 200,000 and 50,000 years ago. Yes, our genetic diversity decreased dramatically during this period. But the bottleneck was probably not a single catastrophic event. It was more likely a prolonged period of environmental stress with multiple population crashes and partial recoveries. Toba probably contributed to this stress. A volcanic eruption that large definitely had regional impacts at minimum. Populations in Southeast Asia probably got hit hard. Populations downwind from the eruption probably suffered significantly. But it probably wasn't the global apocalypse that early theories suggested. Instead, Toba was one event among many in a long, difficult period when being human meant living on the edge of survival. Not because of one volcano, but because of unstable climate, limited resources, competition with other human species like Neanderthals and Denisovans, pressure from predators and diseases. The bottleneck was real, but it was messy, complicated, and drawn out over millennia, rather than concentrated in a single decade of volcanic winter. And here's what's beautiful about this whole scientific controversy. It shows how science actually works. The original Toba catastrophe theory wasn't wrong to propose a dramatic scenario based on the evidence available in the 1990s. That was good science, a bold hypothesis that made testable predictions. What's happened since is even better science. New evidence from archaeology, genetics, climate modelling, and paleontology has challenged the original theory. Researchers have proposed alternatives, tested them against data, refined their models. The picture has gotten more complicated, less dramatic perhaps, but almost certainly more accurate. We're watching human knowledge evolve in real time, getting closer to the truth through argument, evidence, and the constant testing of ideas against reality. That's the scientific process at its best, messy and uncertain, but ultimately self-correcting. The debate continues. New studies are published every year, some supporting the catastrophic bottleneck, others arguing for more moderate scenarios. Genetic techniques keep improving, allowing more precise reconstruction of ancient population sizes. Archaeological sites keep being discovered, filling in gaps in our knowledge of how humans lived during this critical period. Maybe in another decade we'll have a clearer answer. Maybe we'll find new evidence that definitively supports one theory over the others. Or maybe we'll discover that the truth is even more complicated than we currently imagine. But whatever we ultimately learn about the bottleneck and its causes, one thing remains certain. Our ancestors survived it. Whether the population crashed to 1,000 individuals or 10,000, whether it happened over a decade or over 100,000 years, whether Toba was the main culprit or just one stress among many, the result was the same. Humanity made it through. We survived when we could easily have gone extinct. and that survival, however it happened, shaped everything about who we are today. So, here we are, the end of a story that almost never had an ending because there almost wasn't anyone left to tell it. 74,000 years ago, give or take, a mountain in Sumatra exploded with force equivalent to 3 million Hiroshima bombs. The sky went dark, temperatures plummeted, and humanity, our entire species, was reduced to perhaps 3,000 to 10,000 individuals clinging to survival in scattered pockets across Africa and possibly southern Asia. Think about that for a moment. The entire future of humanity, everything that would come after, every city, every invention, every piece of art, every scientific discovery, every person you've ever met or heard of, all of it depended on a few thousand people who refused to give up when the world became uninhabitable. You are their descendant. Every single person alive today, all 8 billion of us, carries genes that survive the Toba bottleneck, genes that were tested by volcanic winter and found worthy, genes that encoded not just physical survival traits, but something more important, the ability to cooperate under pressure, to innovate when old methods failed, to maintain hope when hope seemed pointless. We are all products of the worst environmental catastrophe our species has ever faced, and we're here because our ancestors were tough enough, smart enough, and stubborn enough to outlast a planet that was actively trying to kill them. But here's what keeps me up at night. We survived Toba, barely, but we had no idea what was happening. Those survivors didn't know they were living through a volcanic winter. They didn't understand that their world had been plunged into crisis by an eruption thousands of miles away. They just knew that suddenly, inexplicably, everything got harder. Food became scarce. The climate turned hostile. Children died more frequently, and they had to adapt or perish. They didn't have the luxury of understanding their crisis. They just had to survive it. We're different. For the first time in human history, we can see our existential risks coming. Climate change, nuclear weapons, pandemic diseases, asteroid impacts, artificial intelligence. We can identify the threats that might reduce us to another bottleneck or worse, eliminate us entirely. We have the scientific knowledge our ancestors lacked. We can model the consequences of our actions, predict the outcomes of our choices. The question is whether we're wise enough to use that knowledge, whether we're courageous enough to make the hard decisions that survival might require. The Toba survivors didn't have a choice. They were forced to adapt, forced to cooperate, forced to innovate. The selection pressure was brutal and immediate. Fail to adapt and your genetic line ends. We have choices. That makes us both more powerful and more vulnerable. More powerful because we can prevent catastrophes before they happen. More vulnerable because we can also choose to ignore warnings, to prioritize short-term comfort over long-term survival, to let politics and profit override prudence. But here's the thing that gives me hope. The same adaptability that carried our ancestors through volcanic winter is still in our DNA. The same capacity for innovation that let them survive on the edge of extinction is still driving human progress today. The same social cooperation that maintained those fragile networks of scattered survivors is still bringing humans together to solve collective problems. We are, fundamentally, a survivor species. Not because we're physically stronger or faster than other animals, not because we have natural weapons or armor, but because when everything goes wrong, when the world becomes hostile and resources vanish and death seems inevitable, humans find a way. We adapt, we innovate, we cooperate, we survive. 74,000 years ago we faced extinction and came back from it. That's not just history, That's evidence that humanity is remarkably, stubbornly, almost unreasonably resilient. But resilience isn't invincibility. The bottleneck could have gone the other way. If a few more of those scattered groups had failed, if the volcanic winter had lasted just a bit longer, if our ancestors had been slightly less adaptable, you and I wouldn't be here. Nobody would be here. The story of humanity would have ended before it really began, just another failed species in the long history of Earth. We exist in the timeline where they made it, where enough humans survived to rebuild, to expand, to eventually spread across the entire planet. We're the descendants of the lucky ones, the tough ones, the ones who held on when holding on seemed impossible. That's both humbling and empowering. Humbling because it reminds us how fragile human existence really is, how close we came to never happening at all. Empowering because it shows us what we're capable of when survival demands our best. So if you've made it this far in this journey through humanity's closest call with extinction, do me a favour. Leave a comment letting me know where you're listening from. Whether it's New York or New Delhi, Tokyo or Toronto, you're occupying space in a world that almost never had humans in it. That's worth acknowledging. Hit that like button if this story made you think differently about human resilience, and subscribe if you want more deep dives into the moments when everything hung in the balance and somehow, against the odds, we made it through. Because here's the final thought I'll leave you with. In geological time, 74,000 years is nothing, a blink, a moment. The Earth is 4.5 billion years old. Humanity's entire existence is barely a footnote in that vast timescale. But in that brief moment, we've gone from a few thousand desperate survivors to 8 billion people who have literally reshaped the planet. We've survived ice ages and droughts and diseases and disasters. We've built civilizations that would seem like magic to these Toba survivors. We've walked on the moon, split the atom, sequenced our own genome, all because a few thousand people refused to be the generation that let humanity end. The question now is, what will we do with the time we have left? Will we be the generation that finally fails where our ancestors succeeded? Or will we be the generation that takes humanity's remarkable resilience and uses it to build something that lasts not just thousands of years, but millions? The answer is still being written, and you're part of the story. Sweet dreams.